Hi, everyone. Like I said before, welcome to session 3 of the Intro to AI for AI-driven science on supercomputers. Today, we are going to be digging a little bit deeper into uh, neural networks, building off of what Miriam introduced last week. And today, our instructor is Bethany Lusch. Bethany Lusch is an assistant, Bethany Lusch is a computer scientist at the Argonne Leadership Computing Facility. I'll let her give a little bit more of an introduction about her background and what she does at ALCF, and then she can dive into the content from there. So, Bethany, handing it to you.
Thank you. So I'm in the AI machine learning group in the Leadership Computing Facility. My background is a PhD in applied math. And during my PhD, I started working on machine learning and applying it to dynamical systems, then PDEs, and a variety of science applications. And that's how I ended up at Argonne. And I especially work on using neural networks for surrogate models, for PDE-based simulations, and coupling simulations and AI. So today we're on week 3. So we're in this folder, 03, Advanced Neural Networks. And today's material was written by Corey Adams the last time we did this content. So I want to credit him because I didn't make a lot of changes. Now, last week we learned about neural networks with Miriam, and all of the network layers that you used were what you might call feed forward or dense. So the neurons from one layer are fully connected to the neurons from the next layer. But today we're going to talk about that there are other neural architectures. And I know some people were asking things like, how do you pick an architecture based on your data set? So as sort of a rough overview, this bulleted list is some ways that people might categorize types of data in the context of neural networks. Now, tabular data is like maybe you have a bunch of columns and they don't have any like spatial or sequential ordering. For example, if you're Zillow and you're trying to estimate how much a house will sell for, the columns could be number of bedrooms, zip code, so forth. And a plain neural network could do well with that data. We don't really need like necessarily special layers because those columns are not related to each other in some like special ordered way. Now, image and video data, you have clear relationships in your columns because you have like some pixels being lined up, and that's what we're going to talk about mostly today. Then text data, like a bunch of written English, it falls under what's called natural language processing, and that's what we're mostly going to talk about in the following weeks. But these other bullet points are other kinds of data that we're not going to dive into in this training, but I just want to mention as kind of big picture. So one that's interesting for scientific data is graph-based data, which I think you heard about last week with Nina. So something like you have molecules and you want to represent them as a graph, or maybe you're doing a fluid simulation and it's split into a mesh. That's uneven. You might want to consider that to be a graph, or other things like that. Geospatial data would be like what Troy presented the first week with his weather and climate modeling. And if the data is all evenly spaced on a grid, maybe you could think of it like an image and use some of these computer vision techniques. If the data is not evenly split up, maybe you want to think of it more like a graph or something like that, which would influence the neural network architecture. And then time series or sequential data, that's kind of broad and it can overlap with the text category because if you're like processing a bunch of papers or blog posts, the text is not, you probably don't want to consider it just what you call a bag of words where you kind of lose the ordering of the words. You probably want to think of it as words in some sequence. But time series or sequential data could be totally different, like stock prices or from PDEs or weather or something like that. And then audio, I haven't heard much in the science domain, but things like speech processing, or I recently saw an article about scientists figuring out patterns of migration of whales by recording their vocalizations. So again, this first bullet point, tabular data would be, you might want to use networks with like a basic layer structure like last week. The second bullet point we'll talk about today. The third bullet point are the remaining weeks. And then these other four you might hear about as from the science talks, but we're not going to necessarily cover them in the training, in the like hands-on tutorials. And within computer vision, we're specifically going to talk about convolutional neural networks today, and how they compare to, a little bit about how they compare to vision transformers. But if you want to read more about how machine learning is used in science, here are some papers you might want to click on. And one other interesting part, at least to me, in science applications, is that it's not just picking the neural architecture, it's also what's the loss function. So for example, in physics-informed machine learning, that often means adding onto the loss function some other terms using your knowledge of physics, like your knowledge of an equation or something like conservation of mass. And I think you're hearing about that in some of the science talks as well. And that's the kind of thing I've done in a lot of my papers as well. And today's tutorial, we're going to talk about, we're going to use a data set that's just normal photos, but just to get you in the mindset of science data, here's a picture from Corey Adams' neutrino physics research. So you could, this is from a detector, you can click to read his paper, but you can think about that data sets from things like physics experiments could be thought of as an image, a bunch of pixels all lined up in a grid, even though they're not like a photo from a camera. So today we're going to use this notebook 01 Conv Networks. There's also this second notebook that Corey made the last time we did this, and we don't have time to cover it today, but you can, but I left it in there in case you want to take a look. So like last week and the week before, we can use Google Colab. So I'm clicking here and I'm going to colab.research.google. And I think you've all seen this before, but you can paste in the URL. So here I'm clicking on the notebook from week 3, and it's called 01 Conv Networks. Okay, I'll pause for a minute so that you can all load up Google Colab and open the notebook.
And as a reminder, if you have questions, obviously drop them in the Session 3 Slack channel. And Bethany can get to them potentially if we have downtime as things load today in the Google Notebook, or sorry, in the Jupyter Notebook. And then we'll also have ALCF staff that can answer things in the meantime.
Yes, thank you. Any questions now? I guess I should open Slack in my other window.
So far, nothing's come up.
Okay. All right, then I'm guessing you've probably opened your notebooks, so I'll start talking about it. Now, today we're focused on convolutional neural networks, which is very typical for image data. Now, the first week, when Troy talked about weather and climate, he talked about vision transformers, and that is another approach to image data that's newer. And we're going to talk about sort of bridging those ideas today, because in the remaining weeks, when you learn about large language models, the backbone is a transformer style architecture. And so we want to kind of make some connections. Now, in transformers, they are designed to be applied to sequential data, like a sequence of tokens, and images are not normally sequential data. If you just think of one image, you wouldn't think of it as a sequence. Although, as Troy talked about, you could split up an image into regions, and then you have a sequence of patches. In convolutional neural networks, you do not split up the image into patches, and you make use of the idea that there's a spatial ordering of all of the pixels. Now, this notebook is a lot faster in Google Colab if you use the GPU. So I'm going to click on Runtime, change runtime, and then GPU here. And so now here I can see that it's telling me I'm on the T4 GPU. Now, if you already have access to Polaris, you could run this notebook in Jupyter Hub, or you could do that later for the homework. I think it's a little faster on Jupyter Hub, but it's reasonable in Google Colab. Okay, so one competition in machine learning is called ImageNet. Now, the machine learning community revolves around competitions a lot, which makes it easier to compare methods in a fair way. And ImageNet is a set of images. I think there's maybe 100 different classes, like horse and cat and dog. And every year, people would compete with their AI approach to classify these images. And this plot shows the error rate that different AI models or whatever approach people were using, what their error rate was from year to year. And you see there's a big drop in error from 2011 to 2012. And that year, a neural network approach won the competition. So that was this big deal. It was a big deal that it was a neural network because neural networks had somewhat fallen out of favor. People had somewhat given up on them. And it was a big deal because it was a big jump. Now, in 2012, I was a PhD student in applied math, and I was like sort of in an AI research group from another department and learning about AI, and I remember them talking about this paper. But in my classes, I took like statistical learning classes, and we were not covering neural networks because it was not one of the like most useful techniques at the time. So if you're interested, you can click on this link and read that 2012 paper. And that was using convolutional neural networks. Now, oh no, okay. I'm gonna switch accounts here. It said I ran out of GPU time. All right, we're okay under my other Google account. I was running this notebook a lot with the GPU to prepare. Okay, it takes a little bit of time to load these Python packages, but it's nice that they're installed. So while we're waiting, one reason that neural networks started really gaining traction around then, the algorithms had gotten better, but one big difference was the computational power being more available and bigger data sets. Now, to talk about the pieces of a convolutional neural network, we can use an example image. So here we're just loading an image of the ALCF staff. So surprisingly takes a couple seconds. So here's a picture of our division a while ago in front of one of our old computers, Mira, and I'm right here. And you might recognize more people if you look closely. And we're going to use this image to demonstrate how convolutional layers work. Now, last week you learned about dense linear layers, so fully connected layers going from one layer to the next. You're multiplying by a matrix, adding a vector, and applying some nonlinear function. You could think of a convolutional layer as a special case where you're not multiplying by a full matrix. That's one way to think about it. But I think it's easier if you kind of picture what's happening. Here in this diagram, you have a little image. Let's pretend it's a 4x4 image, 4x4 pixels. And here's a little convolution. I think the green part should be 3x3. So the idea is the green part is the trainable part, and you're convolving it with a window of the image, which if you want, you can look at this equation, or if you've taken some other math classes or physics classes, you might have learned about discrete convolutions. You can also think of it as a linear combination of the convolution, the green part, and the blue part. So let's say for the moment that it's not trainable, let's say this green part is just 4 numbers, 4 random numbers. And then you're applying it to a window of 4 pixels. Then you're doing this multiplication of those 4 numbers with the 4 pixels and adding them up. So a linear combination. Or you could think of it as like a weighted sum of those 4 pixels. And so you can think of this, people call it like a filter. Just like different ways to combine those pixels together. Now, then you shift along. So you apply that same green region, shifted over 1 pixel, and you're doing that same convolution function, combining this like sort of weighted combination of those next pixels. And then you shift along, and you get to the end, and then you wrap around to the next row of the image. So that I know is kind of vague and mathematical, and this formula might not be easy to understand. So now we're going to apply that to our photo of the staff. This line is just loading that image into a tensor for PyTorch. And we're reshaping it so that it's the way PyTorch expects, with like a batch dimension, batch size of 1. And let's create a random convolution for now. Now, so this is a random tensor, just for demonstration purposes. This first shape is the number of channels in the image. In photos, we have 4 channels, red, green, blue, RGB. And after this convolution, I still want to have red, green, blue. So I'm saying I want 3 channels in, 3 channels out. And then we can pick the size of, some people call it a kernel, some people call it a filter. The default here is 15. And then here we're, okay, getting it all set up and multiplying by the image. And this kind of looks like we added noise to that image. And we can also experiment with changing the filter size. So let's say we're looking at just windows of 3 by 3 pixels at a time. And we try that again. This looks a lot closer to the original image. So we, to recap, we generated a random tensor of this size. And you can think of it as having this little 3 pixel by 3 pixel box. And we applied it to the corner of the image and multiplied it on like the first 3 by 3 and shifted over and did it again. So it's sort of a recombination of those pixels. And here it's still recognizable as basically the image, you've got the people. But if we have a bigger window of the convolution, like the 15 by 15, or we could do something in between like 10 by 10, then you're doing this recombination of a bigger window of pixels. And at least to us, it looks less like the original image. It's kind of blurred out. And again, you could think of this as it's doing like a weighted average of a window of 10 by 10 pixels at a time. Now I'm gonna pause. Does this make sense? I know it's a little odd. I see a thumbs up, thank you. Okay. This is like the most important part of the convolutional layer. Now, here we just picked a random filter by literally creating a random tensor. But in a neural network, what we do is let that be trainable. So just like last week, each layer we were multiplying by a matrix and adding a vector, and that matrix and vector are trainable with your gradient descent or a fancy version of gradient descent. Here, these little filters are trainable. So we don't have to decide what to look for in the image because the optimization problem is going to do that for us. But some people have tried to visualize what these filters look like. And there's some idea that the earlier convolutional layers are finding things like edges and like this one might be looking for diagonal lines or something. And later layers are looking for more complex patterns. But basically, they're not what very interpretable by humans. Just kind of roughly we can visualize them. And what I like to think of it as is that it's maybe these filters are looking for certain patterns. And then as you slide the filter along, then you're kind of looking for it everywhere. So for example, in facial detection or facial recognition, you could be looking for a face, but you don't need it perfectly centered in the photo. So maybe you could think of it as a filter could be looking for an eye, but the eye doesn't have to be in the exact same place every time because this filter is scanning along. Now, none of them, since we don't define the filters, probably none of them are literally looking for an eyeball, but that's how I think of it intuitively. And in other methods for computer vision before neural networks, people were often hand defining filters instead of learning them from data. Now, another piece of a convolutional neural network is usually some kind of normalization. And the reason for this is because as you pass data from one layer to the next, to the next, to the next, there can be some instabilities because let's say you pass in one batch of data and it's kind of like an average of 10, and then maybe another batch is like average of 2. It gets difficult to train. And so people started using this idea called batch normalization that's pictured in this first image, where you have a batch of data and you average it, maybe like to mean of 0, standard deviation of 1, before passing it on to the next layer. And I think there's a paper here. I think it's something like, yeah, 2015, when they started using this in convolutional neural networks and getting big improvements. In this plot here, they're comparing, Paige, is there a question?
Nope, sorry.
Oh, okay. I just heard some movement. This black line here is this previous network inception, and that axis here is the steps in training. And you can see it takes millions of steps, but it reaches this decent loss or accuracy. And then here they're comparing some of their newer networks where they're using batch normalization, and they're training to the same loss level as the inception network with fewer steps. And one reason they could do this is because they were able to have higher learning rates, so they're able to make their steps bigger. So that's some motivation. But back to the diagram to explain it. In this diagram, N is the size of your batch, so how many images you're considering at each step. C is the number of channels, like red, green, blue. And for the purposes of this diagram, H and W would be height and width, so the size of your picture, your image. In here, they're normalizing across one channel at a time, but all of the images and the pixels in the image. So that's pretty common, and you'll see it in a lot of tutorials. Now there's also layer normalization, which is more recently popular. And there, instead of averaging over the number of images in your batch, you're averaging over the channels and the height and width, which we're going to use today because it's often used in transformers. So to visualize this normalization, we can apply it to that staff photo again. So again, we set up the photo as a tensor, and then we can normalize and show it. So now we've kind of rescaled all of the pixels, and it's a little harder for us to tell what's going on as humans. 1 second. I want to see how we're doing on time. Okay. So
Bethany, one question
Yes.
that came from the chat was this idea, Ranjo asked, does the filter have to scan pixel by pixel, or can you program spaces, or just filter a subset of the original image?
Oh, yes. Thank you. So you can, the amount that you shift at a time is called the stride. And so that's something that you can set easily in PyTorch. And then if you only wanted to look at a section of the image, I'm not sure if there'd be an easy way to program that. I mean, you could, maybe not easy with the PyTorch functions. And then I should also mention that although conceptually it's shifting along, the way it's programmed is more efficient and more like it's applying it to the whole image at once. Okay, so another common piece in convolutional neural networks is some downsampling. Now, in a convolutional layer, we talked about that you're applying this little window, like 3 by 3, to your image. So you're only looking at features locally at a time. Each filter is only looking at a small patch at a time. And so if the next layer does some downsampling, like reducing the resolution, then that can allow you to gradually have layers take into account bigger and bigger regions of the photo, is sort of conceptually how to think of it. And one common option is max pooling. Now, in this diagram, you've got this little set of 4 by 4 pixels, and we're applying a 2 by 2 max pooling, meaning that it's going to look at windows of 2 pixels by 2 pixels and pick the biggest pixel. So in the green region, the biggest is 100, so that's what gets passed to the next layer. And in the red region, the 184 is biggest, so that gets passed. In average pooling, it's almost the same, except you take the average of the 4. And so we can try that here with the staff photo. This PyTorch function, we're doing max pooling in 2D because it's a little square and a window of 2 by 2. And you can see it sort of looks like a lower resolution, a very like pixely version of the image, but you can roughly see what's happening. And then if you change it to average pooling, I think it will look smoother. So it's a little bit more like how you would actually reduce the resolution of an image. Now, those are sort of the main pieces to earlier versions of convolutional neural networks. But then another helpful idea came in this paper. Let me check the year. Okay, 2015, where they talked about what they called residual learning. Now, people were finding when they were training convolutional neural networks and they stacked up lots of convolutional layers, the improvement in performance was not actually happening the way you would expect. You might expect, oh, if you have twice as many layers, now you have twice as many parameters, and that's a lot of flexibility in this network, so it's going to be really accurate. But that was not happening at the time, and people call this a vanishing gradients problem. So roughly, when you're doing the back propagation through these really deep networks and you're doing that chain rule through all those layers, these gradients were getting super tiny, and I think even like exponentially tiny as you go through all of those layers. And so the training was really difficult. And this paper, Deep Residual Learning, added these skip connections. Here's a diagram. You've got your input X. You're applying this layer. And then the nonlinearity, the next layer. Instead of just continuing like that, you also add in this identity part. So let's say we call this section, this 2 blocks, f of x. So applying this function that is 2 blocks. Now we do f of x plus x. So adding in this x that was before f. And they call this residual learning because it's like these layers are learning just a residual, just something to add on to the input. So instead of going learning how to map from X to Y, you're learning, well, what should we add to X to make it Y? So this, people have a lot of different explanations for why this might be helping. I think you can look at what the gradients look like and say now they're not decaying off so quickly. But we can see from the paper that this helped a lot. So here they're plotting a regular convolutional neural network with 18 layers versus one with 34 layers. And we see the 34 layer network is actually worse than the 18 layer network, even though they have lots of extra parameters. And then on the right, it's the same comparison except with a ResNet, a residual network. So now the 34 layers actually helps. So you can think of this, you can call it adding skip connections, you can call it adding residual layers, and people often refer to these networks as ResNets. And sometimes if you see someone refer to a ResNet, it means like a very specific architecture. I want to pause and check on any questions.
Yeah, we have a couple questions in Slack. One is, what's the difference between downsampling versus convolution?
Okay, so in a convolution, you're applying this filter by doing all these multiplications to windows of the image, and you're not necessarily changing the size of the output. But in downsampling, you're doing like a very simple operation, but the point is just to make it smaller. So like here, it was just the biggest number in the window, and this is like a normal average. But a convolution would do like some kind of weighted average, and then it would shift along so that we don't have the output be any small. So the output's the same size.
Another question, won't normalization solve the vanishing gradient problem?
That sounds reasonable. I think it must be that it was not sufficient. I think that skip connections somehow also help.
Great, that's always on the Slack.
Maybe it depends on the problem, whether normalization or skip connections are sufficient, or if you need both, or one or the other. Okay, so we're gonna put these ideas together into a network. So first, this cell, we're gonna download a data set. It doesn't take too long. You'll notice here I commented out some lines because if you want to run this on Polaris later, you don't have to download it. You could just load it from this folder. So you could uncomment these lines for root and download instead of these lines for root and download. We're going to use CIFAR10 today, which is a data set of little photos, and there are 10 classes. So it's kind of like MNIST last week, except they're real world objects. And this CIFAR10 is small enough that you could run this on probably your laptop, but the GPU definitely helps. Now, and it's popular enough that we can use this convenient function to load it. We can also use these convenient functions to automatically apply some transformations to the photos. So this one, to_tensor, just converts it from whatever the image format is to a tensor. And then data augmentation can be really helpful in machine learning. So let's say you just start with the original photos as they were. If you flip them horizontally, then as a human, we can still tell, oh, that's a horse, even though you flipped it horizontally. So one way to create more data and help the networks be more robust is to randomly flip some of the images. And then this function randomly crops an image between 85% to 100%, keeping 85% to 100%. And then we have it set up to maintain the same size. So it's going to crop it some random amount and then resize it to the original size. And the idea is it's still enough of the image to be recognizable, but add some variety in your data set. And then this color jitter changes the brightness, contrast, and saturation randomly, which could help your model be more robust to random changes like in the lighting conditions or things like that. So this could be relevant for something like a photo data set. And because this set of transformations is in the way we define the data set, it's going to randomly apply these to the images as it loads them up. But then we don't need to apply all these random changes to the test data because we can just leave the test data the way it is and see how accurate the model is. And then we're splitting the training data, so we also have a validation data set. Can pick a batch size. You might want to play with this later. And then add a data loader, which I think you did last week, which will gradually load the data at this batch size. And here's some optimizations to try to load it faster. And then in this cell, we can plot one of the images to have some idea. And some of these are pretty hard, like this. I guess this is a dog. This cell will detect if you have a GPU available, and if so, device is CUDA for an NVIDIA GPU, and otherwise it's CPU. And this wraps around our data loader, so it'll move the data to the GPU as it loads it. And then this cell, we start defining the convolutional neural network that we're going to use here. I'm going to skip ahead and come back to this. In Google Colab, they don't have Torch info installed, so this cell will install it. It's just convenient for a way to see the pieces of your network. Here we're defining the model, and I'll come back to the definition. This part is going to move the model to the GPU if you have a GPU. And then it's going to print the summary of this model we just defined. Now, this is a pretty big, fancy model for this data set. And it is specifically set up based on this paper called ConvNext. And I have it open here in the tab. It's also, this tab. It's also linked in the notebook. This is a paper from 2022, and they were looking at how people are excited about vision transformers. Now, if you recall, transformers are like a building block of large language models, which we'll talk about in the later sessions. And vision transformers is a way to apply them to images. And this paper asks the question, well, are vision transformers beating convolutional neural networks because they're better for images, or is it because of all these other details that they're doing differently? So is there something intrinsically better about tokenizing your image into these little patches and considering a sequence, and then how the transformer will handle that sequence? Or is it just some details? And so it's an interesting paper where they gradually changed a ResNet, a residual neural network, a specific one, ResNet 50. They made various changes and compared the accuracy and computational efficiency, and decided which changes to keep, and then arrive at this accuracy on this data set, 82%, and say it's more accurate than this transformer. Now, this doesn't prove that convolutional neural networks with these sort of modern features are always better than vision transformers, but maybe for some data sets, it's still the best way to go. And so, for example, one thing they experimented with is the kernel size. Now, in convolutional neural networks, a common default kernel size is 3 by 3. So you have a little kernel or filter or window of 3 by 3 and slide it across. But they noticed that in vision transformers, they're looking at much bigger windows of images at a time. So they experimented with making the kernels bigger in CNNs to see if that helps. And it did help a little bit. So the idea is like, hey, maybe that 3 by 3 actually, even though it's like the common practice, is not the best. So we'll do something bigger, like 7 by 7. They changed the activation function from ReLU to GeLU, and some differences in sort of like the sequences of sizes of networks, and other things that are a little hard to, at least for me, explain intuitively. But these tweaks helped them go from 79% to 82%. So some of these ideas are used in the network in this notebook. So it's kind of a complicated network with these block structures, but it uses some ideas borrowed from transformers. And from this cell, we can kind of see the big picture structure. In this model, the inputs, okay. We have first a 2D convolutional layer that we can scroll up here and say, they call it a stem. And so you've got the input, red, green, blue, 3 channels. The number of filters that you're applying, so like number of times you're doing those little windows sliding across, is something that we can pick here. Here we have 32 of them. And then this is a little unusual. It's doing a little kernel size of 1. So it's just considering 1 pixel at a time. And then the stride is is how much you're shifting it along. So this first layer is not doing windows, it's doing 1 pixel at a time, shifted. And then there's a layer normalization. And then we start adding these blocks on in a loop. So this is another thing that you can experiment with, is how many blocks do you want to add? And each is this conv next block, so we can come back to that, followed by a downsampling block. And a detail in this network that you don't necessarily do in other networks is each time a block is downsampling, it's dividing by 2. So like halving, that's common, but also doubling the number of filters. So you're kind of compensating for the spatially smaller, but twice as many filters to scan along. So you apply all these blocks, and then at the end, you've already applied tons of convolutional layers. You keep getting smaller. At the end, you flatten it into 1D, which is common at the end of a convolutional neural network. Then you do 1 more layer normalization, and then you do 1 more linear layer because you need to map down to a vector of length 10. So this is similar to last week. Since there are 10 classes, 10 possible image categories, we need to map down to size 10. And when you piece this all together, you've got that initial stem, which was doing this this one 2D convolution, a normalization, then that set of blocks, 1 more average pooling, and then what they call the head, which is this part where it flattens it out and does the very end. So now I can scroll up and see what the conv next block includes. You have a 2D convolution, layer normalization, more convolutions, and if you look at the forward pass, there are normalizations in between there and this GALU activation function. And then here's the part for the residual neural network. So in this forward pass, you're applying all these layers, and then you also add on that input. So it's sort of letting those inputs skip ahead to the end of the block. And then we can scroll up to the downsampling. So there's a layer normalization, and this is unusual, at least to me. It's a convolutional downsampling. So instead of that like max pooling or average pooling I showed above, now you're learning how to downsample. So that relates to someone's question about the difference between convolution and downsampling. Like, well, here it's a convolutional layer acting as downsampling in order to make the next layer have like a smaller sized input. So that's a lot of pieces for this CNN. And you can see in this printout of the layers how it's repeating these blocks. And with this size, we've got 2 million parameters. You can see the rough size of the model. And these are things that you can play with later. Now, I think this function is similar to what you've seen before. Is a way to evaluate the function. You can put the current version of the model, put it in evaluation mode, loop over all the batches, check what the loss is, check the accuracy. And then this is probably similar to last week. To train one epoch, you're going to loop over the batches. The forward pass is put the input from this batch into the current version of the model. Check what the loss is at this point, then do the backward pass. Now use the backward pass to update the network, reset the gradient. And then here we have a progress bar for if you're impatient to see how you're moving through the epoch. I think cross entropy loss might have been the same as last week. And right now this is stochastic gradient descent, which is like a basic optimizer. You could try changing this like to Atom or Atom W. And you could experiment with the learning rate and the weight decay, which I think you talked about last week. And then this is the cell that takes a while because it's the one that's actually doing the training. And hopefully Google is still, okay, they haven't taken away my GPU yet. So you can see T4 here that you have a GPU. And it's only using, I'm only using 1 GB of the GPU memory. So that might suggest that you can make the model bigger or make the batch size bigger. And here we're looping over the epochs. This TQDM is doing the progress bar. And train 1 epoch with the training data. Then this part is the same except evaluating the model on the training data. I made this only happen once every 5 epochs because it kind of takes a while. And then same, but evaluate with the validation data. So we can see the progress bar here. So far it finished 1 training epoch in 43 seconds. Now it's doing this part where it's just evaluating the current model on the training data. And here, it surprisingly, is taking almost as long as a training step. So that's why I decided only every 5 epochs. It's looping over all of the training data and moving it to the GPU, applying the current model and evaluating the loss function. And then checking how well the model is doing on the validation data only takes 10 seconds because there's less of it. So at this point, the training loss is, well, that's hard to interpret because it's cross entropy. The accuracy is 22% on training data and similar on validation data. So that's better than random guessing because there's 10 classes, but not very good. So this we'll have to leave running for a while. So we can experiment with changing some of the details, and that is what your homework is. For the homework, we want you to change something about the model, like the number of convolutional layers, the number of filters, some other hyperparameter like batch size or learning rate, and compare your validation accuracy to the validation accuracy that we get here running this version for 30 epochs. And you should show the training and validation performance, loss and accuracy for all the epochs. So, or you can leave in my thing of the training's only every 5 epochs, and explain why you think this is an improvement over the original notebook. This paper from 2015 is interesting because it was a big step forward with the residual networks. And this next one is also interesting, the one where they compared division transformers. So you might get some ideas from either of these papers in ways to improve the network. Okay, any questions?
We just had one pop up asking any suggestions on how to tune so many parameters.
Yes. So one thing you can do is if you notice overfitting, which is when the training loss in accuracy is much better than the validation loss in accuracy, then maybe your network is too big, too flexible. So it's overfitting the training data. If the training loss is not very good, then maybe the network is not flexible enough. It can also help to plot the training loss and validation loss and see how like smooth they look. Because, for example, if the training loss kind of like goes down really fast and then plateaus, sometimes that means the learning rate was too big. So it made a lot of progress at the beginning, but then is stuck. Things like that can help. And then I can post, I think in the previous channel, I posted some links to some books online that also have sections talking about how to tune these networks. You also might want to experiment based on a limited number of epochs. So if you want to try like 5 things, you might not want to try all 5 with all 30 epochs. You might want to try with only like 5 epochs. That's pretty common because it can take a while. You can also run these things and walk away and come back. And then if you have access to Polaris, I think this is about twice as fast on Polaris. Any other questions?
There was one question that came up a little bit earlier, asking, the question says, I noticed that in the ConvNext paper that they compared their architectures with VITs, sorry, with vision transformers, sorry, at the same number of flops. Have there been any studies that show the effective data set size and increased compute per model size of convolutional neural networks versus vision transformers?
I do not know the answer. If anyone else knows and want to chime in. I'm guessing that people have tried that, or at least tried it with because in the transformer work, a lot of people are talking about that with these large language models, you can do things like increase the number of parameters and the amount of data, and then kind of predict how the loss is going to improve. So I'm guessing people have tried similar things with convolutional neural networks. But I don't know offhand.
Yeah, Bethany, if I can chime in.
Mhm.
Yes, with convolution neural networks, you generally see this loss saturating after whatever hundreds of epochs, right? But that behavior you'll also see if you keep increasing the training points as well. At some billions of images, you generally see a saturation. Whereas
Okay.
with transformers, it just keeps going for much longer. So the training just keeps improving. That's basically qualitatively, I would say that's the general behavior.
Okay, thank you. I know another comparison between CNNs and VITs. I don't know if Troy mentioned this, but I know when he was working on that weather data, and we were talking about using ResNets, and found it hard to scale them because we were in Troy's application. If you think of the data as being on this grid of the world, and you have all these variables at each point in the grid, then it's like having a really high resolution image that you don't see in photos. And we were running into memory problems, especially with residual layers, because if you're downsampling with the convolutional layers, then that helps with the later layers needing less memory. But because of the skip connections, then we still needed to keep adding back in these dimensions from like the earlier size. So it was hard to make big ResNets for such high resolution data, and vision transformers handled that better.
Wonderful. So I don't see any questions right now, any more questions right now in Slack. And as people have them, as you are working through this notebook and the homework, obviously feel free to drop them in the Slack channel. And Bethany or other folks are will be happy to answer anything. But with that, thank you so much, Bethany, for sharing today.
Thank you.
So what we're going to do now, as we always do, is switch over to our science talk. So Nassar already actually made, he popped his head in to answer Bethany's question, which is very helpful. And I will give a little bit more of an introduction about who he is and what he'll be talking about. So Nassar Ramachandra is a cosmologist with interests in the dynamics of large-scale structure formation. He's also working on the implementation of state-of-the-art statistical and machine learning methods for cosmological data analysis and fast prediction tools as part of the SIDAC4 project led by CPAC. In his talk, he's going to talk about AI for cosmology. So Nassar, I'll hand it over to you.
All right. Thanks, Paige. Let me share my screen real quick. All right. If you cannot see the screen right now, let me know.
It looks good.
All right, thanks. Yeah, thanks for the introduction. Like Paige mentioned, I'm a computational scientist at CPS division at Argonne. And this talk is primarily on the AI-driven cosmology. Okay, so let me give you a quick introduction. So there are quite a few AI for cosmology efforts at Argonne, and the ones I'm going to talk about is really a very small subset. But some of the common themes during the talk is there is a specific caveat that happens with dealing with scientific data sets, is that there are a lot of observations, simulations, or experiments on one side. Observations or experiments on one side, and synthetic or simulation data sets on the other side. And there's usually a connection in between, and kind of trying to explore that connection. How are they related to each other? Can we leverage our simulation capabilities in order to understand the observations? That is the sort of questions that we are generally interested in. Then specifically when we deal with AI, there are certain science requirements. So in a lot of physics problems, we are really focused on trying to get our error estimates on our results. So instead of doing point predictions, we are generally interested more in like probabilistic results. Explainability is a very important aspect as well. It's not just getting answers from our AI frameworks. It's also, can we explain why this is the result, or like what is the sensitivity, that sort of questions. Finally, there's also questions about how do we include physics or our scientific understanding instead of a purely data-driven methodology. So these are sort of things that we are roughly concerned about when we do AI in cosmology. And after talking about that, I'll quickly go over a case study of an image processing pipeline. I saw that Bethany was doing, showing a CNN implementation. So this part should be pretty straightforward application for all of you to go through. But in addition to the classification that you might be used to, there's also issues like regression or data denoising, blending, deblending, latent space representations and all these aspects that we'll just quickly go over. Okay, so first, let me give a quick intro to cosmology. So the universe started about 13.7 billion years ago. That event was called the Big Bang. There was a quick expansion called the inflation phase. And then within the first few minutes, we have the nuclei forming, and the first few atoms in the first 100,000 years. And a few million years, we have galaxies and stars forming. And then in a few billion years, the universe actually starts accelerating. So it's not just an expanding universe that's becoming larger and larger. That expansion is actually speeding up over time. And then we come over to 13.7 billion years, that's today. And when we look at the universe today, the majority of the universe is actually not seen. When I say that, what I mean is there's a huge energy content that is not really observed, but we see the effect of it, and that's called dark energy, and that's about 72% of the current universe. And then dark matter is another content of the universe that we don't see directly, but we see the effect of it in various forms, from galaxies to smaller systems, and even in cosmological scales. And there are different ways of measuring them, and we currently think 23% of the universe is dark matter. And everything else, so that's called the baryons, or the atoms, is just 4.6%. So this includes everything from sun to earth to everything that we see, and that's just 4.6% of the universe. So there's a lot of unknown, and there is a very small part that we can actually see, and even there, like a lot of the physics processes and everything is really not well understood. So pretty big field, a lot of unknowns, very exciting. And the animation that you see here is redshift of 0.7. So redshift is like a unit of distance, or you can also think of it as some unit of time. So this is at certain times time shot. What you see there is the distribution of matter, so distribution of dark matter in the universe. So a large volume in the universe is actually quite empty. These are like the darker spots that you see. And then there's a filamental structure of dark matter. That's how the dark matter is sort of arranged in the universe. And I'm going to run this animation again. And if we keep zooming in, you see that there are some spots that are highly dense, like the brightest spots. Those are the areas where galaxies reside. So those are the densest regions in the universe. And that's where we have galaxies and all the stars and everything. All right, so this is roughly the picture of the universe in current time as well. Then we quantify in cosmology. So we quantify a lot of things, like earlier I mentioned, like the percentage of dark matter or dark energy. Those are all quantified using different parameters. These are collectively called the cosmological parameters. So there's the density of the universe, density of dark energy, density of dark matter, and the cosmological constant. And note these numbers here. So some of these are pretty well quantified. Dark energy is something like 0.6847 plus or minus 0.0073. So this is a sort of error estimates that we are, that's the level to which we really care about. And everything we do, like every research we do, a lot in cosmology, a lot of that is focused towards trying and understanding and constraining these numbers really well. Okay, so that was the brief introduction to cosmology. And how do we actually do this research? This is really a collaborative effort between a large number of folks. There are primarily there are either the observational astronomers, the ones who look at the data coming from the telescopes. So we have telescopes both on Earth and in space. So two of the telescope projects that I work with, one is the NASA SPHEREX, and there's one called the Vera Rubin observatories. Both these telescopes are currently under construction, and they'll be online, I think, in the next 1 or 2 years. So what they do is, and then there are hundreds of these different missions, and all these missions, all these telescopes, basically observe the universe in different wavelengths. So you can observe the universe in radio, infrared, optical, X-ray, or gamma ray, anything like that. And each of those different wavelengths basically give you different information. So some of them might be giving you more information about what kind of matter, like what kind of baryons are in the universe, or some of them can be talking about the dynamics. So different physical processes can manifest themselves in different wavelengths, and that's why we have all these different telescopes looking at the universe. So that's on one side of the research. On the other side, we have all the theorists, the physicists who come up with different models for the universe, different equations to explain how things might be happening. And then there are computational folks who run these massive numerical simulations in supercomputers like Aurora. And we essentially try to replicate the entire dynamics of the universe, entire evolution. So the simulation that the animation that you saw earlier was actually one of these simulations that was run on a very extremely large number of nodes on a supercomputer. And the center plot here, you see sort of the distribution. On the left side, I think you see the distribution of galaxies in the universe that is observed from the telescopes. And the red ones, the red panels are essentially what you see from the simulations. So just by looking at the distributions, you can see that there's a pretty good correspondence between what the numerical simulations predict and what we actually see. And this is sort of one of the important things in cosmology studies. So we have different data sources. So we have data sources that are coming from simulations, data sources that are coming from actual telescopes. There are also different the modes of data. So multimodal data in the sense that, you might be looking at an image, you might be looking through a telescope and you might just be capturing image of a galaxy. Or you might be looking at a galaxy for a long period and looking at the changes in the type of light that is coming in. So that's a time series. Or you might also be looking at spectra of light that is coming in. That could be a vector. I might be measuring how bright the galaxy is, how massive the galaxy is. Those could be scalar numbers. So just like this, there can be various formats of the data. And this is what I can refer to as a multimodal data. Other important caveat is, unlike some of the data sets that you may have actually seen, like the CFAR10 data set, which are basically taken from the internet, right? Or something that is captured from a camera or something. So compared to that, cosmological data set tend to be extremely expensive because the telescopes are billions of dollars worth. The simulations are run on larger supercomputers. They're very expensive. So essentially, all these things come from very expensive science campaigns. The third is a multi-fidelity aspect. So what I mean by that is the quality of the data can differ depending on what kind of sources we are talking about. So an old telescope with low resolution can have a very different data behavior compared to a newer telescope with even in simulations, state-of-the-art simulations can be very different from older simulations. In addition to that, when it comes to a lot of astronomical observations, there are a lot of systematic effects, which means instruments can have certain behavior that are either understood or not really well understood, and they can affect our final answers. And trying to understand how to transfer this knowledge from one fidelity to another fidelity is usually not very straightforward. And finally, data coverage. So one of the things that are important is, so let's say you're training just the CNN that you're dealing with, like CFAR. If you have like 10,000 images of cats and 10,000 images of dogs, and you're trying to do a classification between cats and dogs, that can be a pretty good coverage of the data. That you're covering all angles of the cat. You're looking at a zoomed out version of the cat and a zoomed in version of the cat. Whereas when it comes to astronomy data sets, we don't have that privilege in the sense that there might be a lot of gaps in the data set. You might be looking at some part of the sky and not another part of the sky. You might be looking at so galaxies that are nearby but not really far away, galaxies that are really bright but not the faint ones. So there can be a lot of gaps or the biases in the data sets. And so there is no assumption of fair sampling. And finally, the one that I mentioned was we do deal with simulation data sets a lot. And there is an expectation that in any case where we are using a simulated data set to train, and if you want to deploy this on real world data set, like an actual telescope data set, there is an sort of an inherent assumption that your simulated data set is actually very close to the reality, very close to reality. For instance, I cannot, if I were to do a cat classification network, I cannot possibly train a network based on like cartoons of cat and then actually test it on a real image of a cat and expect it to work. And this is true with any machine learning algorithm. So even in scientific data sets, if my simulations are not good enough, then they're not going to work well with the actual data. Finally, some of the requirements. This is something I mentioned. So we are dealing with something called precision cosmology. So we have extremely high error requirements. There's also this other thing that, astronomy has actually been one of the early adopters of statistical analysis. So a lot of the Bayesian analysis have been tried and tested, and they've been extremely successful. And the other thing is there is actually some advantage to using doing machine learning with scientific data sets is that there is a lot of physics that is already known. There are conservation laws. And if we can leverage those in our networks, that can be a very powerful tool. Okay, so given all this, I'll give some examples and then we go into a specific case. The first one is sort of a more of a traditional framework with the machine learning with an AI tool that is inserted. So this is a classic example of how to estimate those cosmological parameters that I mentioned before. And this is usually done through something called a Bayesian inference. So the plot you see on the right is shows the cosmological parameter constraints. So you have those Gaussian distributions in the top panels. They show each parameter with their errors. And the cross correlations are all shown in the other plots where you see the ellipses. So what we are trying to do is getting a plot like this is actually a very expensive process. You have to run like millions of different forward models in your Bayesian inference, which means you have to evaluate some forward model millions of times. So if that evaluation takes an hour or something, which quite often, if it's a simulation that you have to run for each of those points, it can take thousands of years, which we do not have that much time for. So one thing that you can do is you can have a fast generative model or a surrogate model, which is based on AI. So you run a small set of simulations, train a model, which is what I've shown here. And on the left, I train a model that corresponds to different cosmological parameters. And essentially, it's a mapping from cosmological parameters to my summary statistic. And that summary statistic actually goes into a likelihood function, and then I can calculate the posteriors. And eventually I get my full answer. And this can be extremely fast because these AI systems at inference, they can be very, very quick, right? So I can cut down from thousands of years that I mentioned before to something like half an hour just because my forward model is blazingly fast. So this is an example of something that is a process that is essential and straightforward. It just was a tedious task and it was just sped up from AI. Next, let's see if we can do some discovery from AI methods. One of the things that we often see is when there is a telescope pointing at the sky, you see billions of objects. So there are billions of galaxies and stars that you see. And they're all of different types. So there are spiral galaxies, there are elliptical galaxies, there are galaxies of weird shapes. But more often than not, we don't really understand all types of galaxies because they're all at different stages of evolution. They all have different dynamics. So most of the things a lot of the things that are in the universe are actually not well understood. So we came up with this idea of using a GAN. GAN is essentially a generative model, and it was used to find anomalies. So essentially, you're saying that a lot of the galaxies that you understand are of certain types, um, and ones that do not belong to any of his previously known types, we call them anomalies. And just using an automated GAN network, we were trying to find different types of anomalies, and you can actually see some of the results at the bottom. All the bottom panels are sort of unusual galaxy images that were seen from actual telescope data. In fact, some of these galaxies were sort of very interesting that a different telescope survey might actually go back and look closely into those galaxies and see if there is something curious going on, something interesting that is happening that is causing them to be that different from others. So that's anomaly finding, very useful tool in many scientific research. There's also a lot of hype about large language models and everything these days. Not sure how much you've learned about it already, but essentially large language models belong to this larger class of something called foundation models. And essentially foundation models are all these frameworks that do not have a predefined task. For instance, everything that I mentioned before, maybe you have an image of a galaxy and you're trying to find how far it is, or how big it is, or how bright it is. So that sort of regression task is a very well-defined mapping. Whereas when it comes to foundation models, you do not have a predefined task. So you're essentially constructing a knowledge base based on a huge corpus of data without actually fine-tuning the model to a specific purpose. But that comes in the second stage. So essentially, you're training a bunch of things into a single model. So that's what happens with large language models as well. So huge amount of text data is all fed into these large language models, and then specific tasks about I ask a Python code and I get the code back, or I ask for to write something in Shakespeare style and I get it back. So all those are fine-tuned tasks, but in the at the very core, all these foundation models or the large language models are essentially giant knowledge bases. And so very similar to that, we are trying to build foundation models for cosmology. And here's an example at the bottom. You see this example of a foundation model that was very recently trained on a lot of different types of telescope data. So there's an example where I can put an image of the galaxy and I can ask for what is the spectrum that is coming from that galaxy, and I see some prediction. Or I can ask for different scalar values, like what's the ellipticity of the galaxy, or what's the stellar mass of the galaxy, how far the galaxy is, and all those different questions can be asked to that foundation models, and you can retrieve some answers. And it's interchangeable. Like, in another run, I can give the spectrum as the input and ask for what type of galaxy images I can find. So all these sort of mapping between different modes is actually facilitated by these multimodal foundation models. I won't get into too much details about this, but if you're curious, feel free to contact me in near future. Now let's get into something something more involved. So this is a case study of something called galaxy scale strong lensing. So strong lensing is a phenomenon that happens when you look at certain types of galaxies. So let's say there's a galaxy that is far away, and you're looking at it from Earth, but there is actually another galaxy that is in between that distant galaxy and yourself. And from Einstein's general theory of relativity, the light that is coming from the farther galaxy can actually bend a little bit before coming to the Earth. So when you look at the image, you can actually see sort of a distorted image. You see these very well-defined structures like rings in the background. So all the lower panels in these images that you see, the yellowish galaxies are the foreground galaxy, ones that are closer to you, and the white arcs that you see or the edges that you see, they are the galaxy that is behind, but it's a distorted image because of the gravity of the foreground galaxy. And this sort of problem is very important to understand what is the distribution of dark matter in the universe, or how fast is the universe expanding. A lot of questions can be answered from this. But the problem is that there might be billions of galaxies and only thousands of galaxies might actually be of this kind. So there's like if I'm trying to do a classification, it's not like 1-to-1, right? So each class does not have same number of galaxies. It's at 100,000 to 1, that sort of ratio, that sort of imbalance that is there between what is strongly lensed and what is not strongly lensed. But on the other hand, the physics of this is actually quite straightforward. So we have very good physics models, and because of which our simulations are extremely good. So in fact, all the images that you see at the bottom, they are all simulated because of this very tractable physics models. So in principle, whatever model that we have, we can train it on simulations, and hopefully we can do well with the observations as well. So what we did is we tried to have, instead of like a single deep neural network, we made an entire pipeline of different AI modules. The first module was only tasked with doing an image-to-image mapping. All it did was doing a denoising. So it takes a noisy image and it sort of cleans it up, and you get the second output. That's a cleaner version of the first one. And next one is a source separation or deblending, which means I separate the foreground from the background. So the foreground yellow galaxy is completely removed, and I'm only left with the arc in the third stage, after the second stage. And then comes the detection, which is essentially a classification network where I'm supposed to say whether the arcs that you see is actually strongly lensed or not. And once that is done, if it is actually strongly lensed, then I would calculate some physics parameters. There are parameters like Einstein radius or ellipticity of the galaxy, something that is physically meaningful. I can only calculate it on this subset of data set that was actually classified as strongly lensed. So we came up with this sort of modular pipeline. This was easy because at each of these stages we had simulation data. And also it was like we had the ground truths at each individual stage. And on the other hand, it also makes a lot of the debugging much simpler. Like, if there is a problem in one of the modules, we can quickly address it. And also, if there are newer methods that we want to try, we can only try in certain modules and we don't have to train the entire framework. Yeah, so using that, we had this end-to-end pipeline, and I have shown some of the results. All the original noisy images, along with the background and the foreground galaxies, they're all shown in the top panels. The second panel shows the denoising output. You can see like much cleaner images. And the second one is the ground truth. What we actually see in the simulations. And the third one is actually what's predicted from the AI module. And you can see the DNI structure. And the last two are the true and predicted source separated model. So the third one is the original lens without the source. So that's only the background and not the foreground. And the last panel is what's predicted by the AI algorithm. And then other cool things is you can do a nice representation learning here. So this is this is what's called a T-SNE representation. So essentially, you take all these images, all these data points, and project them onto a 2D screen, essentially. And if your framework does a good job of understanding the latent space, like what is the representation space of all these images, then you can actually start seeing good structure in this latent space. So in the sense that now in this latent space here, if I zoom in at one part of the latent space, I see more of these point objects. Another part of the latent space, I can see these full arcs. So these sort of very clear behavior can be seen if you do the AI training in the right way. And this is the sort of explainability I was talking about earlier. Like we do not have to look at deep learning frameworks as some sort of black box algorithms. You can actually go to the outputs of inner layers and look at their latent space and try and understand what's actually happening in the network. There's also a similar latent space information happening in classification as well. There's also uncertainty quantification. And so one of the things that we did was all our classification came with an inherent uncertainty. And we saw that the places where we had misclassification were also the places where our uncertainty was high. So the deep learning algorithm was actually not very confident in places where it was wrong, which is a very good behavior for a deep neural network. Okay, so with that, I just have a conclusion slide that says there are various types of data modalities. We have lots of different data sources and an extremely large amount of data. So because of all this, AI models are really, really valuable for us. But unlike a lot of the problems that industry or like in general folks might be interested in within scientific AI, there are specific concerns. Many of them have to do with how the physics is handled, or can we explain our results? What sort of uncertainty quantification do we have? But all this can only be possible if you have a very careful experimental design, very careful use of synthetic data, and a lot of validations. Yeah, so with that, I conclude my talk and I'll take any questions. Let me also look at the Zoom to see if there's any chat questions as well.
So I think we have time for maybe one question. And there was one question that came up in Slack that I think is sort of interesting. You mentioned foundation models earlier. Do you have any suggested resources for learning more about them?
Sure. So foundation models, let me look at, I mean, internet is your best friend, really. There's tons of resources. One of the great places to learn anything is actually Hugging Face. So Hugging Face is this open source resource where all these foundation models are generally uploaded by folks, and they're also accompanied by different open source codes which you can just try and run things on. So I would definitely say Hugging Face is a great tool. And I'm not sure if the ALCF data series, actually ALCF also has certain training series that dealt with large language models and foundation models. So you may keep an eye out for that.
Yeah, there's been a lot of work here at Argonne specifically in like the LLM space and also in foundation models, which very fortunately we'll start talking about next week. I think there are a couple more questions in Slack that I don't think we have time to live answer, but what I'll do is Nassar, I'll shoot you a couple questions over email and I'll get the answers back to participants a little bit later on. And with that, I think we'll wrap things up. Next week, we'll be digging into large language models specifically and going from there. So thank you all so much. Have a good day.
Thank you.